Bismillah ar-Rahman rahim. So let us discuss Feistel cipher structure. So this is also known as Feistel network. So the Feistel cipher structure or Feistel network is a building block of symmetric key encryption algorithms or secret key encryption algorithms. Symmetric uh, encryption algorithms or secret key encryption algorithms, right? So this is a building block. So that is why it is called as Feistel cipher structure or Feistel network. And uh, uh, it is, for example, used in data encryption algorithm or data encryption standard, data encryption algorithm, or data encryption standard, most famously known as DES, data encryption standard. So in this Feistel cipher structure or Feistel network, XOR operation is used for the two halves of the data. So let's just before we actually uh, study the structure of this Feistel network, let's first describe the XOR operations. For example, if we have two bits A and B, and their XOR represented by like this. For example, this is 00, 01, 10, 11, all the possible combination for two bits. So this is one here only when two of the bits are not similar. So for example, these are similar, so this is 0 here. The two are not similar, it is 1. The two are not similar, this is 1. And two are similar again, so this is 0. So this is how this XOR operation is defined. So this XOR operation is used, for example, binary operation in the Feistel cipher structure. So uh, let's uh, let's just now study these structures, describe this structure. For example, if we are given a plain text, the plain text is, for example, represented like this. Then the plain text is divided into two halves. Let's call this the left half and the right half. And now, in this cipher, Feistel cipher structure, the plain text goes through a number of rounds. So this is round 0. Let's call this L naught and R naught then, right? So, for example, the right half is fed to a function. Let's call this function f. This is a round function, right? Function f, and the input of the function is the right half and a key, right? So, for example, if we are given a key for this cipher structure, then the key for each round, a sub key is derived from the given key, right? So this key k0 is derived from the key, the main key for the Feistel cipher structure. So the key sub key, this is k0 is the sub key, right? And we have this XOR operator here, and the output of this function f is XORed with the left half of this data. So this completes the first round, right? And then this, after the first round, the halves are swapped. For example, this goes to this side and this goes to this side, right? And now we have again the data after the process data after the first round. So let's call this L1 and let's call this R1. And again it goes the same kind of round here again. So the output of the of this round is then fed to the function f, and again we have a sub key here, suppose k1, and the output of this function is XORed with the left half of the data L1. And again And again, the two halves are swapped. After each round, the two halves are swapped, right? And this process continues. So the dots here show that the process continues. And for example, in the final round again, we have, for example, the data is fed to the function f along with a key, suppose kn, right? And the output is XOR with this half, and here we have, for example, our output, right? And which is again divided into two parts. So let's call this L n plus 1, and this is R n plus 1. So this is basically the cipher structure. We could have called this LC. So LC is equal to, and left half of the LC is equal to this, and this is RC. The cipher, left half of the ciphertext LC is equal to N plus 1, right half of the ciphertext RC is equal to Rn plus 1. So as we used to swap after each part, so normally you will see that these two halves are also swapped like this, but with an additional swap also, so that the ciphertext parts are returned to their original shape. So again, we swap this once more. So here at the end, we have our ciphertext. So this is exactly the same thing as this here. So you see this passes through this like this and ends up on the left side again. So this is LC, and this again on the right side ends up here like this. So this is RC. So basically you can omit this swap here. It's just there to represent the similarity with the previous swap operations in the previous stages. So you can omit this part here, and just you can keep this part here. This is the ciphertext that you essentially achieve. So this is how the Feistel cipher structure works. There are n number of rounds, right? N number of rounds. This is round 1 and 2 and so on, and this is the nth round, and after that you get the ciphertext. So this is the encryption operation. The decryption operation is essentially the reverse of this. So the left half of the ciphertext, for example, it goes through this here, and this right half of the text goes this way. It's processed by this function here along with the key kn. This is the first stage of the description now. For the encryption process, this was the nth stage. But for the for the decryption process, this will be the first stage. The right half goes here in the first stage to the function f along with the key n, right? And the output is fed to this XOR function along with this part of the ciphertext. So the XOR, this part of the ciphertext LC is XORed with the output of this function, and again it goes to the next stage, and finally at the last stage we get the plain text L naught and R naught. So this is the encryption and decryption process. For the encryption process, we move this way, and for the decryption process, we move this way, right? Encryption is like this, and the decryption process is like this. So let us demonstrate this with a practical example, right? Both the encryption and decryption processes. Let's demonstrate them with the help of a practical example. So let's suppose we have a plain text comprising of two parts, right? Suppose we have a plain text OK, right? O and K. So the letter O, the ASCII code for letter O is 79 decimal, is 79 decimal, right? So this is and in hex this is 4f. So this is 4f, 0 1 0 0, and f is 1 1 1. So this is 4f, and k is the ASCII code for k is 75 decimal, which is 4b hex. So this is 40100, and b is 1011, right? So suppose we have this plain text here. So let me write down here actually plain text O. So the ASCII code for O is 79 decimal, which is 4f hex, and this is actually 0100. This is 4, and this is f. So this is in binary, and similarly K is the ASCII code is 75 decimal, which is 04 B hexadecimal, and this is equal to 4 is 0100, and B is 1011. So this is the plain text. So let's suppose we have some key and the sub keys. Let's just go through the two rounds, right? For this example, we are considering only two rounds. So let's suppose we have some key, and from that key we derive a key sub key k naught, which is suppose 10100110, and we have another subkey k1. Suppose the subkey k1 is 10110111. So these are the two subkeys that we have along with the plain text, and we suppose that we have already derived the subkeys from some main key of this encryption algorithm, right? And suppose the function f that we are going to use, let's consider that, let's suppose that it's an AND operation. So the function f can be some complex operation. This function f I'm talking about here. So this function f can be any complex operation, a round function. But for our given example, let's suppose that we are simply performing an AND operation, simple AND operation. So the AND operation, the truth table for the XOR is here, and similarly we can write down the truth table for the AND function also. For example, if we have 00011011, then A and B is represented like this. So this is 0, and this is 1 only when both the bits are 1, right? So this is 1 only here. Otherwise, this is 000, 0 and 1 is 0, and this is 0, and this is 1 here. So for our encryption operation, let's suppose that this function here is simply an AND operation, right? And this is the XOR operation that we will perform here. And we have already supposed our the plain text to be O and K letters. And the keys, we have already K0 and K1 supposed the keys. And we will perform only two rounds for this encryption operation. So uh, now the encryption process. So let's go through that. So this is going to a function f, and which is the AND operation here. So this is AND, right? And along with the key k naught, right? And the output of this AND will be fed to an XOR operation, right? And the output will be swapped, right? Like this. So let's perform this AND operation first here with this left half L naught. This is the L naught. This is the R naught. So and let's call this the output here, the F naught, right? The F naught. So F naught is basically equal to the AND of R naught and K naught, R naught and K naught. So the R naught is here. R naught is equal to 0100, this part, and 1011, and the K naught is the key. This key 101000110, right? And the function is AND operation. So this is an AND operation here, right? So of both these uh, bit patterns. So 10 is 0, and of 10 is 0. This is 1. This is 0 0 0 0 0 and 0. So the output, this is output of this function, and this is f naught. We call this f naught. So the f naught here is 0 0 0 0 0 0 right? And this is then XORed with the left half of this plain text L naught. So the L naught here is 0 1 0 0 and 1 1 1 1, and then this is XORed with. And for the XOR operation, the output is 1 only when both the bits are not similar. So this is 0 and 1 is 1, this is 0 and 1, and this is 1, this is 0 0 and 1 and 0. So this is basically the output here, which goes here, right? So this is L1, this is R1. So the R1, the output, this is R1, right? The output here is R1. So this is 0 1 0 0 1 1 0 1 0 1 0 0 1 1 0 1. And the left half, the L1 is the same, is equal to L1 is equal to the R naught. So this is 0 1 0 0 1 0 1 1. So we have completed one round of the encryption process, right? So let's go through the second round now. The second round, again, we feed it through the AND operation here, and the output of this AND is XORed with this L1, right? And then this will be swapped, right? And this will give us the ciphertext, right? So here the key is then K1. This was K naught, and this is K1. So see, R1 is uh, is processed with K1 to the AND operation. So this was R1. So let's write that again. R1 is equal to 0 1 0 0 1 1 0 1, right? And the key K1 is supposed to be 1 0 1 1 0 1 1 1, and this is AND operation here. So R1 and K1 go through this AND operation, R1 and K1. So this is 1, so this is 0 1 0 0 0 0 0. So this is 0 0 0 0 1 0 1, right? So this is, let's call this F1 is equal to 0 0 0 0 and 0 1 0 1 0 1 0 1. So now uh, uh, we have shown a swap here, and if we are finishing our encryption process here, so for the finish we have an extra swap, right? Or otherwise we just do not need to swap both these parts. The output here is just the left part, and the output here is just the right part, right? So let's perform as we have done this swap here, so let's perform another swap, right? And this will be the left half of the ciphertext and the right half of the ciphertext, right? So uh, this part here is the right part, 0 1 0 0 1 1 0 1. So 0 1 0 0 1 1 0 1. So this is the right half of the ciphertext, and the left half is just to needs to go through this XOR operation yet. So this was F1, and this is to be XORed with the L1, L1 is 0 1 double 0 1 0 1 1, and this is the XOR operation, right? So this is 0 here, this is 1 1, and 1 here, 0 0, and 1 0, right? So this comes out to be uh, the this part, and this ends up here. So this is 0 1 double 0, and 1 1 1 0. So this is the ciphertext that we have obtained, and if you look at that, this is 4 and E hex, and this is again 4 and D hex, and this is the letter N, decimal 78, this is decimal 77, this is letter N, so this is letter M, right? If we use the ASCII code for conversion. So our plain text OK has been encrypted using these two rounds of the cipher, Feistel Cipher structure, using the two rounds and using the AND operation as the function into this ciphertext. So this is our ciphertext here, N and M. So if we want to decrypt this ciphertext, we need to run this process in reverse. So this part of the ciphertext will be fed through here, and this part of the ciphertext will be fed through here, and this will go through AND operation along with the key K1, right? And then XOR here, and then again the process will go on like this upwards, and finally we will obtain the plain text. So um, so the decryption process is essentially the reverse of this encryption process. So let's go through the decryption process as well, given this ciphertext now. So let's again consider the ciphertext is also then uh, divided into two parts, right? So this is the left part of the ciphertext, and this is the right part of the ciphertext. And the ciphertext as it was, let's write it down: 0 1 double 0, 0 1 double 0, and 1 1 1 0. And the right half of the ciphertext: 0 1 double 0 and 1 1 0 1, right? So let's look at this again: 0 1 double 0, 1 1 1 0, and 0 1 double 0, 1 1 0 1. So this was letter N and M. So this will again go through the same process. So the AND operation here, we use the AND operation, right? AND operation along with key. Now remember that the key is now K1. The last key used now is now the first key that we are going to use. This is the process being run in reverse. So the key K1 will come first, then the key K0. And if you are using N rounds, the key Kn will come first, then the key Kn minus 1, and then finally key K0. So the output is XORed with this, the left half of the ciphertext. And then we swap both these parts, right? Right? And run the process again. So let's see. First this, the RC is 0 1 0 0 1 1 0 1, right? And the key K1 that we used was here: 1 0 1 0 1 1 and 0 1 1 1. And we are to perform an AND operation, right? AND operation here for both these bit patterns. So 1 and 1 is 1 1, this is 0, this is 1, this is 0 0 0 0 and 0, right? So this is F1 here: 0 0 0 0 0 1 0 1, right? And this is to be XORed. So this is F1 here, and this is to be XORed with LC. LC, the left half of the ciphertext is 0100 and 1110, right? So and this is an XOR operation here. So this is 110100 and 10, right? So here we get the L1 and this is the R1. So the R1 comes out to be, this is R1, right? So this is the output is R1 here. So this is 0100 and 1011, and the L1 is equal to RC, right? So this is 01001101. So this now again goes through the same process, the AND operation, and this is XORed with this here, and this will give us the plain text, right? So the key here is now K naught. So the R1 is processed through K naught, R1 and K naught through an AND operation, K naught, and the K naught that we used was 1010 and 0110, and this is AND operation, right? So this is 1 and 0 is 0 and 1. This is 0, 0, 0, 0, 0 and 0. So this is now F naught. So we are running reverse. This was F1, this is now F naught, and this is 0, 0, 0, 0, 0, 0, 1, 0. And this is XORed with L1. So this was F naught and L1 is this 0100, right, and 1101, and this is XOR operation. So this is 0 XOR with 1 is 1 1 1 1 0 0 1 0, right? So in the manner we swapped here, let's swap here again, right? And as we are just to finish with 2 rounds, so let's swap once more. And then this is our plain text, L naught and R naught. So you see L naught is the output of this XOR operation. So it is this, right? So this is 0100 1111, and R naught is simply R1. So this is 0100 and you see that this is 4F hex and this is 4 uh, uh, 4B hex, right? So this is letter O, right? ASCII code for O, and this is the ASCII code for K, in hex, ASCII code in hex. So we have recovered plain text from the ciphertext by running the Feistel cipher structure in reverse. So you see that if you compare both here, so this was F1 here, right? And in the decryption process, the F1 here is 000010. So here again, at F1 is this stage was 0001 here at this stage, right? So what we got the output of F at the last stage we got here at the first stage in the decryption process, right? And then if we go upward, this was L1 and this was R1. So if you see, L1 and R1 are the same as here, right? And then we have this output here, the F uh, uh, F naught is the same here, 000010, as the F naught output here. And finally, we get the uh, uh, plain text O here, right? And the second part of the plain text key here, right? So this is the encryption process, and this is the decryption process. We run the encryption process in reverse to retrieve the plain text. Uh, I think that concludes our discussion of the Feistel cipher structure.